In our previous video, we demonstrated how to move an electromagnet around using a Core XY gantry. In this video, we're going to add chess pieces to it to create a fully functional smart chessboard. Let's have a little recap. The stepper motors are controlled through the XRP board's GPIO pins via drivers. The electromagnet is toggled using a transistor circuit powered through a buck converter. We added an LCD screen that is connected via the XRP board's I2C compatible Quick Connect port to add a user interface and display moves. One of the most challenging problems we faced was enabling a piece to move without colliding with other pieces on the board. Certain moves, like castling, a knight sleep, or capture, often had their paths obstructed by their pieces. Finding an optimal route through these obstacles was tricky. Our solution involved first moving the piece toward the center of the current square in a direction based on its position on the board. From there, we used a rectangular movement pattern to guide the piece safely through the gaps between other pieces. Finally, we recentered the piece on its destination square. Here's the gantry control code, which you can learn more about in the first episode. Now we can combine it with a chess engine. The Micromax chess engine, an open source framework by Harm Mueller, was used for the chess engine. Micromax is computationally light and can run well on embedded processors, like the XRP's Raspberry Pi RP2350.
The engine returns a string for the move. For example, the string e2, e4 would mean moving a pawn from square e2 to square e4. Mueller's chess algorithm initially performed well. It used a recursive approach to look 5 moves ahead, consistently identifying the best possible move. While this worked effectively against human opponents or other chess programs, a problem emerged when the engine played against itself. It would always play the same game. This happened because the algorithm deterministically selected the same best move at each turn. To address this, we introduced a degree of randomness into the decision-making process. At each decision node, if multiple moves were nearly equal in evaluation, the algorithm would randomly choose between them. By applying this randomness at each comparison point, the engine was able to generate a different game each time. It's important to note that this challenge involved a trade-off. While it improved variability, the added randomness slightly reduced the overall strength of the engine. As we started testing our project, we quickly found out that there needed to be a precise balance between square and piece size, magnet strength, board friction, electromagnet distance, and piece weight for the game to function properly without the pieces crashing into each other. We found out that using an abrasion-resistant polycarbonate for the board with a polyester fabric on the bottom of the pieces was the perfect frictional combination for the precise piece movements. By adding electronic components to the top of the pieces, we are able to add enough weight to stop the pieces from repelling each other, while also adding a cool and unique breadboard component theme to the board. This project has been a fun challenge for us. Make sure you check back to see the other pieces of this project, and check out the write-up on Maker.io linked in the description below.